I would like to give credit to people who contributed and give a slightly historical background. So it's not so FinFET is actually not a new device. It was introduced in 2000. Their press release was in 2011, manufactured in 2012, but it has a long history going back all the way to 1990s. And the first Stockley FinFET demonstration was done by this person, Hisamoto-san. He was a researcher at Hitachi, and at that point, this was, remember, 1990, and the gate lengths were in the micron level, but still he showed this showed that when you decrease your body thickness, even at that gate length, if you decrease your thickness of your fin, again he was still operating in this micron level of width. So what he showed was if you go below that 0.3 micron in width, he could get nearly ideal subthreshold slope even at those very high oxide thickness and very high gate lengths. So when I was preparing this lecture, I looked him up. He is still, there's a very long longevity of people usually who work in Japanese companies. They tend to stick around in a company for a long time. So he's still at Hitachi, but what he did was between 97 and 98, he was visiting as a researcher at Berkeley. So he picked up his old research from 10 years back or 8 years back, and he tried to continue when he was back in a university setting. Probably he got more freedom to work on it. So he published, what he did in 1998 was initially, that point, his first paper was at a gate length of micron, and what he did was he really scaled down his device. So this paper is an IDM paper in 1998. If you read it, it has an excellent figure. It has only few figures, 3 or 4 figures, but all of them are really good figures and really impactful figures. And what he shows is that he was able to scale his fin width down to 20 nanometers. So he used a spacer based process, and he could pattern this very a very narrow fin of 20 nanometer, and that really allowed him to scale his gate length. So he could scale his gate length down to 17 nanometer, and it still had a near ideal subthreshold swing, because again this device scales as long as you scale your width and your length together. So he was able to scale his width, and that allowed him to scale this gate length. So this was 12 years back, and people were already making 30 nanometer or 20 nanometer FinFET devices. And then there was a much bigger program at Berkeley. They had many people working on it who tried to improve on it and make even smaller FinFET devices. But an important thing is all of these were done on a SOI substrate, because it's easier to define that fixed fin on a SOI substrate, and they were scaled gate length, but they were these huge source drains. So they were scaled gate length devices, but they were not really scaled pitch devices. So they had a huge footprint even though they had a small source drain, because again it's very difficult to do source drain engineering in a university environment, to do all the sophisticated implants. So, but still the proof of the concept existed back in all the way back in 1998, and what people since then industry kind of got interested and picked it up. 2002 they made a paper from TSMC that used all 3 gates, the top gate as well, and then they started to make these FinFETs on bulk substrate, which are cheaper and easier to get. And there have been many demonstrations since then, and people have demonstrated, made even thinner and thinner fins, and that has allowed them to scale the gate length as well. and the record currently is held by this Korean university, which has made these FinFET of 3 nanometer gate length. So quick question here. So we talked about 22 nanometer technology. So that has a current of, let's say, 1.5 milliamp per micron. So every time you reduce your gate length, you get at the same voltage you'll get a higher current, right? Or you get less delay, I would say. Let's talk about delay. So let's if you had this device, the delay would be your switching time, would it be twice better, would it be the same, or would it be worse? Yeah, so it turns out is actually similar or not any better than what we have currently today. And the reason is that even though you can make this small device, the problem really comes from all these source drain resistance or these extrinsic resistance which don't scale with your gate length. So I am a little short on time, so what I want to do is very quickly talk about the device implications of making this fin device. So we talked about process technology so far, but even on a device level there are many challenges, or there are additional things which come into play because you have this 3D device now. So one of the things that comes into play is your so again, there are many things. I want to highlight 4 of the main issues. So the first issue is related to fin quantization. So remember I talked the critical things in a FinFET device is its width, and that really determines your electrostatics. So you want to keep it uniform. Your height, you want to keep it taller, but it's limited by how good your edge technology is, how whether it falls before you can actually make the device. The fin pitch, again you want to space them as close to each other, but that's limited again by your source drain implant, because you want to implant them at an angle, so you're limited by how close you can place these fins close to each other. The problem, or the kind of the unique feature, is that in a planar device, right, you have your gate, you can make any width of your device. Your width could be anything. When you have a FinFET device, each of your device has each of your fin gives you a transistor width of twice your fin height and your fin width, and your width essentially is only, you can have 1 fin, 2 fins, 3 fins. You can't have like 2.5 fins, right? So it's quantized, and people, especially who are in the analog designers, they really want to make layouts by hand, as we saw in that A6 chip. They want to lay out their feature by hand. So you really can't do that when you have a FinFET device. You can't pick up arbitrary widths. Similarly, all of that system on chip, it requires these multiple and non-quantized widths, and becomes very difficult to do that if you have a FinFET device. So here's an idea. I can't make multiple fins, but I can make maybe fins with different heights, so I can quantize my I can maybe get another variable to give me less quantized width. Again, this looks good on cartoon, but it's very difficult to do if you want to control 2 different edge backs and give you 2 different fin heights. But on paper, at least you can. This is one work around that problem. Another unique challenge with your fin device is that even though you start with one crystal orientation of your wafer, you get multiple crystal orientation in your device, because you have these side walls, and say you had a 100 wafer with this 110 cut. If any of you has worked on a fab, this is the most standard wafer you get. But if you depending upon whether you cut your fin in this direction, or whether I pattern my fin in this direction, or I pattern somewhere in between, I'll get these multiple crystal planes on my side. So if I pattern this perpendicular, I'll get that 110 plane. If I pattern it at a 45-degree angle, I get that 100 plane. If I pattern it somewhere in between, I get this other plane. So I'm starting with one wafer, but I'm getting these multiple crystal planes on my fin, again because I have this 3D device. So again that opens up a whole new field, because your silicon is not the same in any direction. Yes?
Do people actually pattern it other than just like...
No. So Sam gave a lecture yesterday, right? He said you just pattern straight lines nowadays, right? You don't pattern multiple directions. But the important thing is, which direction should I pattern it in, right? Should I pattern all of them this way? Should I pattern them this way, or should I pattern them in midway, right? So that's an important decision I need to make. Which direction do I need to pattern them? All of them. Right, and that's a trade-off, because silicon is not the same in any direction. So this is a band gap quick recap of your E228 or your semiconductor solid state device physics. So silicon is an indirect band gap material. It has this conduction band along your x axis in your K space. It has a valence band which is centered in the middle of your band structure, and it has your conduction band essentially looks like these 6 lobes, and your valence band also looks like these different light hole and heavy hole bands. And whether you make your channel in this direction or you make in this direction, you get very different curvature of these bands. So you'll get a very different electron mass, you'll get a different hole mass especially. So the point being that you can by having these multiple surface orientation, at least you'll have one surface orientation on the top and another one on the side. You'll get different mobility of your electrons or your holes on the side, and different on the top. So this is just showing the experimental data of electron and hole mobility. So in fact all that quantum mechanics that I just briefly browse through is true, that you get different electron mobility along different, if you whether you are on 100 plane or you are on 110 plane. Similarly you get much different hole mobility. The way it turns out actually not that bad. So the orientation that people currently use for the side walls is this 110 orientation. So that 110 orientation actually improves your hole mobility quite substantially, and it's not as good for NMOS though, so it degrades your NMOS. So it kind of degrades your electron transport, but it improves your hole transport. But to start with, our hole transport, your hole mobilities used to be much lower compared to your electron mobility. So silicon has a hole mobility in a transistor, what you get is around 100. Your electron mobility, what you get is 400. The hole mobility you get is around 100. So moving to this 110 side walls, that hole mobility improves by twice, while this one degrades by 0.7 times or 0.6 times. So it turns out your electron and holes mobilities become comparable to each other if you actually use this 110 side wall. Yes.
What is the thickness dependence?
It is dependent on thickness as well. So actually your quantization changes your band structure as well, and the more quantized you are, typically your mobilities degrade. So the more thinner channel you have, your mobilities degrade. You also have more roughness when you have a thinner channel, so your mobilities degrade as well. So it has a thickness dependence as well. So if you make very thin fins or you make very thin, ultra thin body devices, you will get mobility degradation. The point I want to emphasize on this figure is that people use this orientation, which is good for PMOS, is bad for NMOS, but overall it turns out not to be as shabby. Ideally you would want to keep your electrons on that axis and keep your holes on this axis, but again that requires you to pattern these fins. One is in this direction, another is going this direction, and there's no way you can achieve that with current lithography. So again, tapering this fin, so making it conical, that's again not too good for your mobility, because what you're doing is maybe you're on this particular crystal plane, and when you go to any different crystal plane, and depending upon how much taper angle you have, you will degrade your mobility again. So this conical fin, it's again not good for your mobility or your on current for your device. So this is another limitation. Another limitation that you get is the third limitation is around your parasitics. So when you have a fin device, you have this tall fin, you have this tall gate wrapping around it. What it means is that you get much higher fringe capacitance between this tall gate and these tall fins, and FinFETs have much worse parasitics, which is really bad for analog and even bad for your digital circuits. And there are some simulations analysis, and they say that the parasitics capacitances are in fact, so all these other capacitances where you get because of these tall gate and these tall contacts being close to each other can be much higher than the actual capacitance you get between your gate and your fin. So parasitics are again much worse because of this 3D natures of this device. So again, there's no free lunch in this industry. So whatever you do, you face complications. One way to improve your electrostatic is go from a double gate device to a tri-gate device, because a double gate device you have this nitride spacer, so you get extra fringe capacitance due to this gate coupling with that nitride spacer. If you have a tri-gate device or you use that top surface, you kind of get rid of that capacitor, so you get some relief and you have slightly better parasitics. The last challenge is how to obtain multiple threshold voltages in a FinFET device. So again, to revise some of your device physics, your threshold voltage in a MOS cap or a MOSFET is given by this simple formula, and it's determined by your flat band voltage and by your oxide capacitance, and it's related by these formula, and primarily it's a function of these flat band voltage, which is the strong function of your doping. So traditionally the way people used to control your threshold voltage is by just changing your doping in your substrate. So you could, if you want to make your PMOS, you change the doping of your p-type carriers. If you have NMOS, if you have PMOS, you change the doping of the channel, so you change the doping of your n-type channel, and similarly NMOS, you change the doping of that p-type channel. So but since what we did in our FinFET was we got rid of that body doping, so how do we enable these multiple VT devices? Turns out these multiple VT devices are very important, especially if you've done any course in analog, you make any analog circuit, you need devices with multiple threshold voltage, and your key parameter to tune your threshold voltage is now gone. So what do we do? So we discover, what people try to do is, look at this equation again, and then they say, maybe VFB is gone, maybe I can play with this oxide capacitance, or I talked about that fin width is a key parameter, so maybe I can make fins with multiple widths. So one way to tune your VT in this kind of process is to have these multiple dielectric thicknesses. So you could have a dielectric thickness of 5, 10 and higher, depending upon whether you want to have a low VT or a medium VT, or so this is one way you can tune it. Again, it looks very easy on paper, but it becomes very difficult to do when you want to enable multiple gate oxide thickness in one device. Another thing which as we talked about, your fin characteristics are very dependent on your width of your fin. So one way you can tune your VT is have these fin of multiple widths, but these width is essentially defined by your spacer. So you need to have two spacer processes. When you define your lithography, is determined by that width of that spacer in that spacer defined lithography. So you'll need multiple of these spatial lithography steps if you want to have these fins with different widths. So there's no easy way out of it, and so far even Intel has released just chips on microprocessors which don't use these are all digital chips, but when you try to do analog circuitry using a FinFET process, it becomes very hard because you have your quantized width, you can't really make multiple threshold voltages. So okay, let's summarize our learning. So we have talked a lot about FinFET today. Hopefully, you guys have picked up some of it. So let's assume you are a CEO of a foundry and you want to decide whether I make the FinFETs like Intel made it, or whether I make more like a vertical. They made it like a cone, but if I make it more vertical, so what I want you to do is fill up this scorecard. All I'm looking for is which is better, whether it's this vertical one, the theoretical device, or whether it's this actual device that Intel made. And executives, CEOs love scorecards, so we want to give them a scorecard how we rank these two different device design in terms of these different metrics. So let's start with the electrostatics. So which do you think has a better electrostatics? So this design wins in terms of better electrostatics. The vertical fin is better. Let's see in terms of mobility, which one is better? So it has crystalline planes along the vertical sidewall, so it has better mobility. So again, two smileys for the vertical device, two sad faces for the conical fin. But let's talk about collapse of fins, which has better structural stability. Yeah, because it's a more cones, of course, that's why they put it on the road. You can't really kick them off. So looks like there's one smiley face for this guy. How about corner effects? Which one is better? It has no corner, right? In terms of okay, this is a hard one. I didn't really touch upon. So in terms of doing implants, which do you think is better? Yeah. So if you're at an angle, you can implant from the top, and it will still go in between because it's like a tapered fin. So again, in terms of implants, this one is better. So it has three smileys compared to two rat faces. So maybe it's not as bad to make this kind of device. So so finally, at the end of it, I started with the press release. So it says, we'll get into this tablet space. We'll reduce our power consumption significantly. What do you actually get? So I'm hoping, Mark Bohr said that I'll get 37% faster and whatever, half the power. Let's see actually, so how much benefit do I actually get? So there's this website, Tom's Hardware. It's a UK based website. What they do is they just take microprocessors and they run very common tasks that you do on your laptops. So it turns out it has that advantage. So this is your Ivy bridge, which is based on that 22 nanometer technology, and this is Sandy bridge, which is based on your 32 nanometer planar. So it does have advantages for doing that, but not as much as they claim. So it's better. As you can see, maybe it's 2-3% better, faster, but definitely not 37% faster, right? So take those claims at face value. Always examine them more carefully. But maybe they were really trying to get into the tablet space with this. Maybe maybe the performance really is not optimized, but the power really is, right? So maybe I'm getting half the power for the same performance. So how many think that will be true? So you think that the power for the same performance would be much lower, right? Okay, so how many people agree with Bing that the power would actually be lower? Raise of hand. Better, worse. Okay, so let's look at actual data, right? So the power for the same performance is better, but it's not half. it's better by a few percent. So there's no easy way out in scaling. We talked the first class that I started with, scaling is dead. I'm trying to prove the point again. So they it's kind of, I'll give them some credit because they do this TikTok design. So what they did from Sandy Bridge to Ivy Ridge was they take the same design and just ported it over to a FinFET process. But you really need to optimize your design for your device as well. So maybe the next chip that will come out, their 14 nanometer, will have better of these matrix. But currently, nobody is selling tablets using their process. Yes.
How much smaller is the chip?
The chip is in fact smaller, yeah. So that part of the Moore's law is still valid, that you have you can print twice the transistor in the same area, but you don't the transistor does not cost half the price anymore. In fact, it costs more. Neither does it perform faster anymore. A lot of your transistor improvements are washed out by your interconnect, so your interconnect performance really does not scale, and so your transistor gains in a lot of cases almost by 30. What that looked on that inverter that Mark Bohr showed, when you actually make it to a microprocessor, it becomes just 30% of that inverter gain. So a lot of these things are washed out, and there's not so there's advantage, but it's not that much. Problem set is due on Tuesday. Nobody apparently is asking any questions or coming to the office hours, so I'm hoping everything is okay. Or maybe you haven't started, but how many people have actually started or looked at it? Looks okay, or okay, alright. Well, post it on the forum or come to office hours. You will hold it on Monday. I usually do it after the class, so you're welcome to drop by. Right, thanks.